Inverse function introduction. Today I'm going to introduce the concept of inverse function. First, let us start by saying what the function does. Well, the function takes an input, say a number of x, and does something to it. It calculates something using this value of x. For example, it might calculate the answer 2x plus 3. So this would be a particular function. Let us call it function f. So what it does to the value of x, it first multiplies it by 2 and then adds 3. Now, the basic understanding of what the inverse function to this function is to understand that what has been done by the function f should be undone by its inverse. So how to undo what has been done to the value of x? You remember x was first multiplied by 2 and then 3 was added to it. So if you want to undo these operations, you have to do them in reverse order, but not exactly those operations, but reverse operations or the inverse operations, better word, to those. So what is the inverse operation to addition? Of course, it's subtraction. And what is the inverse operation to multiplication? Of course, it's division. So instead of doing first the multiplication and then addition, we will do them in the opposite order, or in the reverse order. So first we take a number and subtract 3 from it, and then divide the result by 2 to obtain the answer. So in the inverse function, the x value, the input, is converted using this process. First, subtract 3, then divide the answer by 2. So first the subtraction, then division. The operations that we have performed here, or which the function performs, are coming in the reverse order, and they are reverse they are inverse operations to the original operations that appear in function f. Okay, so you may have noticed my notation. The notation for the inverse function is as follows. We read it f inverse. F inverse. It's not read f to the power of -1, as I will talk about it in a while. Just wait for it. Okay, so the basic understanding is undoing what has been done. The inverse function undoes what the original function did. Now, we can make our understanding even better if we imagine each of those functions as a function machine. So understanding the concept of inverse function using the notion of function machines. You may remember these function machines. Here they are. This red one is the function machine representing the function f, and what it does when x is fed into it. When you feed in the value of x, it multiplies it by 2 and adds 3, and it appears on the output. And then when you have this output and you feed it into the second function, it takes it and does something to it. It first takes away number 3, the value of 3, and then divides the answer by 2, and there is its output. So let us now try to see what happens if we have two such functions and we combine them, or we say compose them to form a composite function like this. So let us try the first function value that is of interest here, the function value, the x of 0. Okay, so I take x being equal to 0, and what the first function does to it is it multiplies it by 2. 2 times 0 is 0 plus 3, and at the output we get 3. So 3 is at the output of this function after feeding number 0 in. Now this number 3 is then taken as the input for the second function, so the same number here, and what it does is it first subtracts 3 to get 0 and divides it by 2 to get 0. So what you notice is this: 0 was inserted into the first function, and it also appears here on the output of the second function. Let us try how it works for a different number. So let's say we'll take the input of 2. So x equals 2 now. I take 2. 2 times 2 is 4 plus 3 is 7. So at the output, I get 7. 7 pops out here at the output of the first function. Then the number 7 is fed into the second function. You see that they are connected like this. So what is on the what appears here from the red function goes directly into the blue one. So number 7 is fed into the blue function. 7 minus 3 is 4 divided by 2 is 2. So at the output, I get the same number that was input into the first function, 2, 2. Okay, let us try the third value. Let us take the value of -1, say. Okay, so if I input -1 here, what I get is 2 times -1 is -2 plus 3 is just 1. So 1 is at the output of the first function. And when it is fed into the second function, 1 minus 3 is -2 divided by 2. Well, you get -1. So whatever you input into the first function, when it goes through it and through its inverse, should appear without any change at the final output. So this is what happens, or what the inverse function does. This is very important to understand, that it undoes what has been done by the original function f. So now let us talk a little bit about the notation. Notation used here. The inverse function of function f is denoted as f inverse. I read it f inverse because it's not f to the power of -1. So beware of the following. F inverse of x is not 1 over f of x. It's just the convenient notation that we use, but the meaning is different. It's not the reciprocal of the function f of x, but it's just the inverse. Function f of x is here. Here is the inverse function f inverse of x. This is how we read them. Now, let us look at the following. And the following thing here is the question. Does every function have its inverse function? Well, the answer is no, it doesn't. And the example here is the function y equals x squared, which doesn't have an inverse. The reason for that is the following. Imagine that you have this function machine here that represents the function f, which converts x to x squared. So this is the function here in this example. So imagine that you input the value of 1 into it. So let us write it here. I will use red color again. 1 is input here. What is on the output? You get also number 1. Okay. Now, if you take a different number and say you input number -1, what do you get on the output? -1 squared. Well, it's also 1. And now you see the problem here. If you wanted to have an inverse to this function, it would have to work as follows. It would have to take number 1 as its input and output number 1, but at the same time take number 1 as its input and output number -1. Since there are two input values that result in one output value, you see it here, then the inverse would not be able to decide what to output if you feed in number 1 to it. What to output, number 1 or -1? There is an ambiguity. And this cannot happen because any function has to have a unique output for every number you feed in. You cannot have two outputs for the same number that you feed in. So there could not be the inverse. Well, what you can see here, this function y equals x squared, is a special kind of function which we would call a function which is not one-to-one. So we may imagine, if we sketch a graph, a very quick sketch here. So this is the set of axes. This is x and y coordinate system, axes x and y, and the x squared function is like this. Its graph is a parabola, okay, like this. And what it does, it converts number 1 to, say, number 1, but also number -1 is converted like this to the same value of -1. Okay, so this is the trouble, because this function breaks the horizontal line test like this. For example, if I draw a horizontal line like this one, you see that for the function value of 1, there are two x values which result in it. And therefore, this function is not one-to-one. If you had to imagine its inverse, it would be ambiguous in its function. It could not decide what value to assign, what value to output for the input of 1. Is it 1 or -1? Who knows? Okay, so not every function has its inverse. Only some functions do, and those that do are called one-to-one functions. They have to be one-to-one for them to have inverse. Okay, now let us talk a bit about properties of inverse functions. Well, this is quite extensive, so I'll start with the first thing here. When one composes the original function and its inverse function in both ways, one has to obtain the identity function. Identity function is the function y equals x. It means identity function is the function which converts x to x. As you have seen here, any number that was fed into this combined composite function, any number in the input appeared without any change at the output of the composite function. So as a whole, this composite function represents an identity function. It outputs the same thing that was input into it. Now, there is this interesting thing. Whenever you compose this function and its inverse in both possible ways, you should get identity function. So it says here, f composed with f inverse of x is x, but also f inverse composed with f of x is x. So therefore I have this picture here. This first picture represents the function f inverse composed with f, while this function here represents the function f composed with f inverse. Okay, so you may well remember that this has the meaning of f inverse of f of x, while this had the meaning of f of f of f inverse of x. Okay, so this is the way how we write composite functions, and let us check now whether everything works correctly here. So let us start with some values here. I'll take blue color and let me input the value of 3 into this function. If I input 3 here, what I get at the output is 3 minus 3, 0 divided by 2 is 0. When I input, well, if I take this 0 and feed it into the second function, okay, what it does is 2 times 0 plus 3. Here I have the output of 3. So number 3 was converted to the same number 3. Let us check again. Let us take a different value. Let's say I'll take the value of 7. 7 minus 3 is 4 divided by 2 is 2. And if this value of 2 is input to the second function, 2 times 2 is 4 plus 3 is 7. So you see the same number. And the third case, or the third situation, let me check the number 1. 1 minus 3 is negative 2 divided by 2 is negative 1. And when negative 1 is input here, at the output I get minus 2 plus 3 is positive 1. So you see, those two functions are the inverse of each other, actually. Okay, because when they are combined or composed both ways, they behave as the identity function. Okay, now this was the first property. It's written here. Now let us go for the next. This one is the most interesting actually, and it's about the graph of the inverse function. The graph of f inverse is the reflection of the graph f in the line y equals x. Okay, so what does it mean? Let us look at this here using the graph that I have prepared. This green line is the line y equals x. Why? Say this is 3 and this is also 3. 2 here, 2 also here. So you see, this really represents all the points which have the same values of both coordinates x and y. Now let me take a red color and try to describe or create or draw the graph of the red function. I will choose the points that were fed into it. So the number 0 was fed into it, and at the output I had 3. So if I take 0 here, at the output I should get 3. So this point here has the coordinates of 0 and 3. Okay, so it's the first point of the red function f. If I take number 2 and input into it, I should have 7. So 2 is here. Here we have 4, 6, 7. This is 7. And the point here is 2 and 7. Now, if I take negative 1 and input into it, I should get at negative 1 here, I should get positive 1. So the point would be there. Negative 1, positive 1. Okay, so you see this function goes through these points. Now let me show how the inverse function works. So if let us look at this point with coordinates 0 and 3. The inverse function works the opposite way. It takes 3 and at the output it has 0. So I will draw its graph in blue. So it should have the point 3, x value is 3, and the y value should be 0. So this point should lie on the inverse of the function f. So it's the point with coordinates 3 and 0 here. Okay, next point that it should contain is the point with coordinates 7 and 2. 7 and 2. So let me take 7, so it's here, and 2. It should be here. Okay, there we have 7 and 2. And finally, let us take number 1 as x, and at the output we should have negative 1. So this is 1, and here we have negative 1, so this point there. 1, negative 1. Now look at these points that we obtained. So you may notice that the point that we started with at the red function, at the function f, was 0 and 3, and the corresponding point for the inverse was 3 and 0. What can you say about them? You see that they are each other's reflection in this axis y equals x. So if you change the coordinates of any point, it is reflected by this axis. You see it works also for the point 2, 7. Its coordinates are 2, 7, it's here, and its reflection in the y equals x line is here, and it's the point 7, 2, which has swapped coordinates, that you have changed the order of coordinates. The same goes for this point, minus 1, 1, and 1, minus 1. You see their coordinates are swapped like that. Okay, now let me complete this. If I have to complete, I should be able to draw the graph of this function. So let me connect those points. I should go like this. I should be able to connect them in this way. Perhaps it would be best to have it like this. And let me take red color for this line and make it a little bit thicker. And let us then draw another line which connects these points here. And there I should have it. It should go through them in this way. And maybe make it a little bit longer so that it goes through those points without any problem, and make it blue, say, okay, and a bit thicker. So here we have the graphs of functions. So the first function, the red one, is the function f, and the blue one is the function f inverse. Okay, and both have the graphs which are each other's reflection in the line y equals x. Okay, so now let's get back to this mind map and uh, return to what we want to say. So if any point with coordinates x and y is on the function f, or is part of the function f, then the point with coordinates y and x is the part or is a member of the function f inverse. Reflecting the function in the line y equals x has the algebraic effect of interchanging x minus x and y. Okay, so for example, if you have, and this is something that I will talk in a second video, if you have a function y equals 5x plus 2 and want its inverse, all you have to do is to exchange x and y. So what you get is x equals 5y plus 2, and then try to evaluate y for it. Okay, so this is what the inverse really does. Now, another property of inverse function is the property about domain and range. These are the properties connected with domain and range. So it says that the domain of the inverse is equal to the range of f. Well, the domain of the inverse, so what you can input into it, is exactly what comes out from the f. So the values that are at the output of f form the range of f, and all of them are input into the second or the inverse function. Therefore, the domain of the inverse function must be equivalent or equal to the range of the original function. Okay, so it is written here, the domain of the inverse is equal to the range of the original function f. At the same time, since you can do it also this way, it means that the domain of the function f has to be the same as the range of function f inverse. The reason for that is that whatever comes out from the inverse function is fed into the original function, and therefore this has to be true. The domain of the original function is the same as the range of the inverse function. Okay, now what is a self-inverse function? There is a special category of functions that we call self-inverse functions. Any function which has an inverse and whose graph is symmetrical about the line y equals x is a self-inverse function. So here I have a picture of a self-inverse function. This red function, function f, which actually it could be, for example, reciprocal function. Okay, reciprocal functions have graphs of this form. This function has this property that whatever point is on this function, for example this one, also its reflection is on the same function. Therefore, this function is its own inverse. If you reflect it in this axis, you get the same function. This is the meaning of the of what we say when we say that it's symmetrical. If it is symmetrical, that it means that if you reflect it on this line, you get the same function, identical function. There are many self-inverse functions. This is just one of them, and we will have some exercises in which you will be asked to work or decide whether something is self-inverse or not. Okay, so much for this concept. Now the final remark. Domain restriction as a way of finding the inverse of a function which is not one-to-one. So you may remember here that the quadratic function y equals x squared was a function which is not one-to-one and therefore cannot have its inverse. If you wanted to find the inverse of the quadratic function, you would have to reflect its graph. So this, imagine that this is y equals x squared. You would have to reflect its graph, and what you would obtain then is this blue thing here, but you see this is not a function because it breaks the vertical line test. It's just the relation. It's not a function. So if we wanted to work with the inverse of the square, then of course we could, but we would need to be very clever. Instead of taking the whole function y equals x squared, we would just take the function y equals x squared where x is greater than or equal to 0. So it means we would just wipe off this part of the red parabola, and what would be left would be just this part, this right-hand part of the parabola, right half, and then reflect this. If we reflected this in this axis, what we would obtain would be this part of the blue parabola, and the bottom part would not appear there. And actually, there is a function which is an inverse, which is the inverse for this kind of function, for the function y equals x squared, x is non-negative. And this function is, as you may have guessed already, it's the function y equals square root of x. And this function actually works as the inverse. Whatever you take as x here, for example, number 3 squared is 9, and when you take the square root of 9, you get again 3. So these two functions would be each other's inverse. And the process that we did here is called domain restriction. So you can make a function one-to-one by restricting its domain. And when you do it, then you can have its inverse and you can work with it.